Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about how to determine the coefficient of viscosity by falling sphere resistance method. In our previous lecture, already have discussed another one concept of capillary tube method for determining the coefficient of viscosity. Now this is another method which is known as falling sphere resistance method for determining the coefficient of viscosity. So viscosity basically we have studied in our starting lectures during the properties of fluids, and like how to define this viscosity. We can define this viscosity as a measure of fluid's resistance to flow, you can say, and also you can say that it is the internal friction of a moving fluid also, you can say. And when the fluid is moving, so that we can say whether the fluid is high viscous or less viscous. If it is a high viscous, then it can move very slowly, and if it is a less viscous, it can move very fast. And this is this is about the concept of this viscosity, and we know that it is denoting by mu, and the unit is Pascal or Newton second per meter square. So these are things are about viscosity. And now coming to this method, falling sphere resistance method. So this method is based on the Stokes law. Okay, and this method actually based on the Stokes law concept, and which according to this law we can say the drag force is there. Actually this concept is based on the drag force, and this drag force is nothing but the force on a small spherical movement, or you can say this a small sphere is there, and which is moving with a constant velocity, we can say. Suppose let consider a small sphere which is moving with a constant velocity v, or you also can consider through a viscous fluid, and that concept is to coming under the Stokes law. So calculation of this coefficient of viscosity by this method, falling sphere resistance method, is also based on the Stokes law. Okay, so this is the important point. Now here, as per the Stokes law, the formula actually for this already was defined in a different topic. So this F equal to, we can write 3 pi mu and velocity v, or you can write u, whatever it thinks, into d. So this is one equation, we can mark it. And here if you see the parameters, what is there? Force, this is the drag force is there, equal to, we can write 3 pi mu is the viscosity, u is the velocity or velocity of the sphere, and d is the diameter of the sphere, you can say. Okay, now this is about the sphere. Now when the sphere attains at a constant velocity u, the drag force is the difference between the weight of the sphere and the buoyant force acting on that. Okay, I'll tell you that details of that. First let's see how we can determine this coefficient of viscosity in this experimental setup. So this is the experimental setup what we have to consider here, and this part is actually, this outer part is this is a constant temperature bath. Okay, so this setup is made in such a way so that the temperature will be remain constant inside this container. Okay, so that the temperature of this liquid or fluid which is present here, it should not be changed with respect to time. And why? Because if the temperature of this fluid is changing, then of course the viscosity of the fluid is going to be changed, because viscosity is directly proportional to the temperature. So that this outer layer or this boundary of this container is like a insulated type, or it is a constant temperature bath type is there. And this is the fluid which is present here, and let drop a sphere on this. Okay, so this is the sphere which is, let put a sphere on this, and initially the sphere will be moved with a high velocity, we can say, and with a high speed, you can say, and after that it will be moves slowly. When it is started moving slowly and with a constant speed, then from that point we need to consider. So suppose we have dropped the sphere at this point, and at least at starting we have seen that it is moving very fast, and at a point it will come like from there to it will move with a constant speed, we can say. So from that point we need to pick it. So suppose this is the point where it started moving with a velocity u, and the same velocity u it is continuing, and let another one point here. Okay, yeah, this is the 2 point of the sphere what we have considered, and the distance between these two position is L. Okay, these are the fixed mark. I mean, this is one point and this is another one point, and this is about the sphere. So it's moving inside this liquid with a velocity u. Okay, now, yeah, now this is the Stokes law what we have identified, and as I told you that the drag force is the difference between the weight of the sphere and Bion's force acting on that. Now when it is moving, if you see, when the sphere is moving, there is some forces are acting, there are some forces are going to be acted on that sphere. What are the forces is going to act on this? Now one thing is, there is a drag force which be going to be acted on this. Okay, so drag force is nothing but when the sphere is moving, so it will be act opposite to this one. This is one point. And one more thing, the weight of the sphere, which is always moving downward. Okay, the weight of this sphere is always moving downward position, we can say, and the drag force which is acting on this, that is upward. Okay, this is one thing. And another one thing, though the sphere is is in the liquid, in a closed container, it's there inside the liquid, so there is a Bion force is also going to be acted on this, Bion's force AP. So these are the forces are going to be acted on the sphere. So, and what are the other parameters can be acted on this? Let's see. Like means what are the things we can consider as a parameter here, like diameter of this container and the length of this position of this. So let me write this some points. So length, one thing we can write L. This is the L, the distance traveled by the sphere in the viscous fluid. So you can say the length. This is actually the distance traveled by the sphere in the viscous fluid. So this is the length, you can also say. And next is you can say the rho s, that is density. We know that rho equal to density, and rho s is nothing but density of sphere. This is density of sphere. And similarly, another one rho we can consider, that is rho of fluid. Density of, this is the density of sphere, and this is the density of the liquid. Density of liquid and or fluid, you can say. And this is weight of the W. As I told, there is a weight of some weight is there of the sphere, so that is weight of sphere. And along with that, as I told, the force of Bions or Bion force which is acting on the sphere. Bion force acting on the sphere. And one more thing, the time taking, like when the sphere is we have considered at this point, so what is the time is taking to move from this position to this position. So let's write T is the time taken. T is the time taken to cover by the sphere to to move, to cross the length or distance L. So these are the some parameters are there which you can consider. This is one portion. Next, what we can calculate, now we need to find out the velocity. So the velocity of the sphere, we can write V or we can write U. So velocity equal to, we know that what is the distance or what is the length traveled by the with respect to time. So that's this one we can write what is the length traveled with respect to time. So that is L by T. This is one thing. Now next, W. One is velocity, next is W in the sense weight. Weight is nothing but, we know that weight of the sphere, that is equal to, we know the W equal to mg. So and m you can write in terms of rho and V. That means if I write rho equal to mass by volume, then mass equal to rho into volume. So I can write rho V G, density, volume and G. And here also we can write volume, what we can write, pi by 6 dq into rho. Rho is nothing but rho of the sphere and into g. So this one, equation 1 I have given. Let give this is equation 2. Okay, and this is actually volume of the sphere. Volume of the sphere, this is pi by 6 dq. Okay, this is weight. So next is, as I told, that the number of forces are acting on this sphere, just we need to identify what are the forces are acting on that. And next I can write the buoyant force. So buoyant force is nothing but, it is denoted by FB, and which is not is equal to the weight of fluid was displaced. The weight of fluid is displaced as per the Archimedes principle, if you have studied this, and this also we have already discussed in the during buoyancy and flotation. This concept was already discussed. So FB also we can write in terms of, you know, what is the volume of the fluid displaced. Volume of fluid displaced. The same concept I can put it here. Weight of the fluid displaced equal to volume of the fluid displaced into density of the fluid. Density of the fluid into G. So volume of the fluid displaced is nothing but pi by 6 dq, and here I can write the volume of the fluid rho f into G. So this is our FB. So this one we can give equation 3. So volume of the liquid displaced equal to volume of the sphere. Okay, this one, volume of the fluid displaced is nothing but volume of the sphere. That's why I've written this one. Okay, this is volume of sphere. Now we got here a few equations. One is weight of the sphere, another one is the buoyant forces. So these two equations we can use in our upcoming concept. So what is the next target we need to do? Now we know that in this the Stokes law is applying, or the concept of Stokes law is there to identify the coefficient of viscosity by this method. So, and Stokes law is related to the drag force. Okay, and so drag force we can write, because we need to make it the equilibrium condition. Okay, for equilibrium condition we can write the drag force equal to, we can write weight of the sphere, weight of sphere minus what is the buoyant force, FB. So you can write F equal to W minus FB. So this one we can give equation 4. Okay, now this is our formula. So what we'll do, the next is we'll just put the value of this W and FV in this equation, so that we can write now put the value of W and FV in this equation, and the value of even F also. This is the value of F, which is drag force. So we can put all this value here. So that is 3 pi mu u d. Sometimes this equation also will be written in this way, 6 pi mu u r. In terms of d, it will be written r. So that is d equal to 2r. So it will be multiplied in this way. Okay, so you should not be confused about that. So this is this, and next is pi by 4 dq, and this is rho s into g, and minus w, this fb equal to similar thing, only rho will be there. So similarly pi by 6, and this is dq, and this is rho f, and this is g. Okay, so all these things are multiplied here. Now what we'll do, we can take common of this, pi by 6 dq g can be taken common, so that rho s minus rho f. Okay, and actually what is our intention? Our intention is to calculate or to identify the value of viscosity, coefficient of viscosity. So what I'll do, I'll just keep this mu at the left hand side, and remaining terms I'll take it to the right hand side, so that I'll get pi by 6 dq into g, and this is bracket start rho s minus rho f divided by 3 pi mu u d. Now if you see, we can conclude this in such a way, mu equal to this 6, we can take it to bottom, pi can be cancelled, so that we can write g dq bracket start rho s minus rho f bracket close, and in the denominator it will be 6 into 3, that is 18, pi already cancelled, and this one you can write 18 into u, and this d is there, this d you can cancel one d square, so that it will be 2 g d square. So this is our final answer. Mu equal to g d square rho s minus rho f by 18 u. This is another one equation. I hope 4. Now 4 already given, so we need to mark it 5. Yeah. So this is the equation, okay? And this equation, like in this equation, the values of d, u, and rho s, rho f is supposed to be known, so that the viscosity of the liquid can be identified or can be calculated. So I hope you understand this concept. Like it is a very simple one. There is nothing critical or difficult in this condition. Only thing is we need to see what is the concept of this coefficient of viscosity and how to calculate. Calculation is resistance method, and this falling sphere resistance method is nothing but based on this Stokes law. And Stokes law is talking about drag force when the sphere is moving. When the sphere is moving with a length or with a velocity u and along in the viscous fluid. So that is about the drag force, and that is F equal to 3 pi mu u d, and from that it started. So that you need to when it is moving, when the sphere is moving in a liquid, so there are some forces are going to be act on that, and that is already we have discussed this kind of concept previously also. So what are the forces are there? Now one is the drag force, another one is the buoyant force, and another one the own weight of this sphere is there. So these are the three things I have considered just, and then finally based on this this equation we just kept all this value, and finally we found this equation. So I hope you understand. If you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.